Сейчас проверим.
Да, есть.
Звук есть, да? Очень хорошо, спасибо. Today we will discuss different conditions for the property of holomorphic non-extendability of a domain at points of the boundary. So let me recall the formal definition. So consider a domain in Cn and a point in the boundary. We say that D is locally connected at zeta. If there exists arbitrarily small neighborhood of the point zeta, in Cn, that is simply connected, such that its intersection with D is simply connected. That's it. So it's first definition. Second definition is the following. In this case, if U is locally connected at zeta, we say that U is holomorphically, if D is locally connected at zeta, we say that D is holomorphically non-extendable at zeta. If for every U such that the intersection is connected, if for arbitrary small U such that intersection is connected, there exists a function holomorphic function on the intersection that does not extend analytically to the point zeta. And here arbitrary small may be replaced by small enough if, and moreover, we can say the following. There exists a neighborhood U such that this is connected and we have this. And of course, if we have a smaller neighborhood with the same property, then of course one of the same function defined in the bigger neighborhood is okay for this one. Okay, that's it. And we say that if one or two holds for every boundary point, then D is called locally connected or holomorphically non-extendable at the boundary. That's it. Now let us consider. Let us make the following remark. Let D be a domain of holomorphy. For simplicity, we suppose that it is locally connected at the boundary. then this implies that D is holomorphically non-extendable. Because we can take function f for which this is domain of holomorphy, this function is okay. This function satisfies the second statement. So now let me state the following theorem. Okay. The same statement holds if and only if a domain D is a domain of holomorphy if and only if it is holomorphically non-extendable. So we have seen. So I will not prove this. The other part is the most tricky part, and I will not prove it. I will just give the statement. And we have seen last time a basic example. So example. D is the complement of Cn to a ball of radius r. Euclidean ball of radius r. That's it. And here the norm is Euclidean. And the argument was the following. Given a point of the boundary of the ball, say the north pole, we remarked that there exists a sequence of holomorphic disks convergent to a disk centered at the given boundary point and which is tangent to the boundary. And this limit disk punctured at the tangency point lies entirely in our domain D. And this was the abstraction, this was the reason for, so this is, the calculation is that D is holomorphically extendable at each boundary point. And the reason for extendability was this. And due to this fact, we have taken a whole family of such disks, and we have using them, we have constructed the Hartog's domain. But we do not need Hartog to construct Hartog's domain. But the statement is that whenever you have such a family of disks, holomorphic disks, the limit point, the point here, is a point of holomorphic extendability, always. Yes. And even if this domain has fractal nature, which doesn't allow us to construct immediately Hartog's domain. So now let me introduce the following definition. I would like to generalize this argument to a general setting when we have when the holomorphic disks are replaced by so-called compact holomorphic surfaces. So let us introduce the corresponding definition. So let n and r be natural number, and r is less than n, and let us consider W a domain, a bounded domain in CR. This means that its closure is compact, and let phi be an injective holomorphic map into Cn, injective holomorphic, and the rank of differential is equal to R. At all the points, it is in immersion. And the holomorphicity at the boundary means holomorphic extended holomorphicity on a bigger domain than W. That's it. And then phi of the closure of the closed domain is called a compact holomorphic surface in Cn. And now we are ready to state the theorem, but still I will need some notations. So recall that if given a positive delta, we call the polydisk delta x sub delta is a polydisk of radius delta, delta, etc. Delta centered at the point x. And we denote for every subset k in Cn, we denote k power delta as a union through all the points x in k, these polydisks, delta of x delta. It is kind of delta neighborhood of the subset k. Now, let us introduce the following, still the following notation, the following definition. So we will be dealing with sequences of convergence compact holomorphic surfaces of the end of situation like this. And we would like to define what is convergence. Here is the definition. Definition. A sequence of subsets M and K subsets, and we say that Mk converges to M if for every positive epsilon there exists a big N such that for all the K greater than N we have the following inclusions. Mk lies in the epsilon neighborhood in the sense of the set A, and M lies in the epsilon neighborhood in the sense of the subset K, Mk. That's the definition. And now theorem. Which is called Benke-Sommer continuity principle. So it is about the following situation. Consider a sequence of consider domain D and the sequence of convergence the compact holomorphic surfaces lying entirely in D. And let so they are compact holomorphic surfaces. And let us assume that they converge to some limit set as k tends to infinity. And let us assume that their boundaries also converge to some compact subset in D, converge in the same sense. That's it. And let us, and then the statement is the following. Statement is the following. So let us let rho 0 denote rho of gamma, the gap between gamma and the boundary. What is the gap? It is the supremum through x lying in gamma of R such that delta, the polydisk radius R centered at x, lies infinum. So let me define properly. Infinum through x line in gamma, which is R at x0, R of x0. And now, what is? And let us recall what is R of x0. R of x0 is the maximal radius of polydisk centered at x centered at x, lying in D. R of x, sorry. Let me recall this definition. So given a point x in D, let us consider the biggest polydisk contained in D, is centered at x. And its radius is called R of x. Is supremum of R such that the corresponding polydisk centered at x lies in D. That's it. Now, so we have defined the gap, rho 0. And now the statement is the following. So it's a continuity principle. So the continuation of the statement of the theorem. Then for every small value sigma lying between 0 and rho 0, for every point zeta lying in the line in S in the limit set, for every xk sequence of points in the convergent circles convergent to this limit to this point x, the following holds. For every k big enough, for every holomorphic function f in D, each holomorphic function in D so for any k big enough, we have that xk lies in delta of x sigma, and for each holomorphic function f on D extends from xk to the corresponding disk holomorphically. That's it. So the picture is the following. So here is gamma, here is gamma. So we mark the gap from the boundary. And we consider the limit surface. The limit of the surface S. Pick any point x. And now let us construct around x polydisk of the radius almost the same as this gap. The statement is that every function holomorphic in the whole domain extends holomorphically to this polydisk. Extend means that its germ at xk extends there. That's the statement of the continuity principle. And this is an easy corollary of the previously proved Cartan-Tulin theorem. So proof is the following. So let us consider an auxiliary. So let us take an epsilon. So let us take an epsilon less than or equal, epsilon say equal to rho 0 minus delta sigma over 2. This means that if we have sigma, we have sigma plus epsilon in the middle, and we have rho 0. That's it. And now let us fix G being epsilon neighborhood, epsilon over half epsilon neighborhood of gamma. The closure. Then Then the boundary of Sk lies in G for every k big enough. For obvious reasons, because by definition of convergence. Now, you have the following trivial observation. Claim. The holomorphic hull of the boundary contains the whole surface. It's just by maximum principle. Every holomorphic function on Sk achieves its maximum modulus here in the boundary. Nothing special. And we have this. But what do we have? By Cartan-Tullin, for every x line in the holomorphic convex hull of the boundary, for every function f holomorphic on D extends holomorphically to a neighborhood of x. Of which neighborhood? Of x, and here is rho prime, and where rho prime is the gap between the boundary, between these boundaries, Cartan-Tullin. And what we know about this rho prime? We know that it is greater or equal than the gap between the G and the boundary, because Sk is contained in G, right? And this guy is clearly greater or equal to the gap of gamma minus epsilon power over half. The gap of gamma is rho 0 minus epsilon over half. And we have this inequality for rho prime, right? And we know that in the rho prime neighborhood of x, any point of the surface of this the hull, the function extends. And this holds for x line in the Sk, because Sk lies in the convex hull, right? And we have the following situation. We have here xk conversion to x, and we know that the function extends holomorphically to a big polydisk centered at xk of radius rho prime. At xk can be made arbitrarily close to x, and it is clear that xk is epsilon over half close to x. Then this big disk will cover this one, and we conclude that the function indeed extends holomorphically there. That's the end of proof. So now, what corollary do we have? Corollary is the following. This will be theorem 1. Corollary. Let in this theorem one has that zeta lies the point of limit surface of limit set, which needed to be a surface. This point lies in this intersection. Let in theorem one can say like this. That this intersection is non-empty. Then D is not domain of holomorphy. The proof is straightforward. The proof is straightforward because what does it mean that this intersection is non-empty? It means that we can take zeta line in this intersection. And we conclude by this theorem that every function holomorphic in D extends to this big polydisk centered at X. What about notations? It is X. It is X, sorry. It is X.
Yeah, maybe.
Sorry.
You need to change those, like,
Okay, sorry.
it's okay.
Sorry.
It's quite tricky.
Sorry. Okay, and that's the end of proof, because we have taken this X, we obtain that the function, every function holomorphic in D, extends holomorphically to a neighborhood of X. And this is impossible if D is the domain of holomorphy. Yes. Do you have some question?
No, I'm just. Okay.
Yes, because for the function, we take the function defined. Yeah, of course. Yes, please feel free to stop me in any place.
Yes, it's okay.
Okay. Okay. Now, what's next? Next, we would like to introduce using this. So we have seen that holomorphic surfaces play an important role in studying of extendability of domains and being of holomorphic convexity as well. And we would like to introduce the notion of Levy convexity or L convexity dealing with convergent compact holomorphic surfaces. So definition. A domain G is Levy or L convex at a point in the boundary if we have the following. If for every compact holomorphic surface S passing through X means that this is surface in the bind space N, for every sequence of holomorphic surfaces of compact surfaces SK convergence to S and with boundaries convergence to the boundary of S and the boundary of S being compactly contained in D. So SK are considered to should lie in K in D. So we assume that the convergence sequences, the surfaces lie in D. The limit surface does not lie in D, it contains a point of the boundary. And but the boundary of S, the limit surface S, does lie in D, and this is the limit of the boundaries of SK. Then, sorry. I would like to erase this. For any like this, one has that the surfaces should so the complement of the surface to D is non-empty for every k big enough. So, what is the picture for this definition? The picture is the following. Let us imagine we have a domain like this. Here is D from this side. And we took a holomorphic surface through some point x of the boundary. And its boundary is perfectly inside D. The claim is, the definition is the following, that suppose for every surface through X with boundary line in D, and for every sequence of surfaces Sk convergent to S, with boundaries convergent to the boundary and boundaries for the boundaries line in D, suppose that this is possible. But suppose that for every such surface, the convergent surfaces Sk do not lie entirely in D. They intersect in the complement. Then in this case, if this is true for every convergent sequence of surfaces, that they indeed contain a point of the complement, then we say that D is L convex at X. That's it.
So it basically says something like that.
So the contrary is this. If we deal with D being the exterior of the ball, then we have a point X in the boundary. We take some holomorphic surface, so for example holomorphic disk, and then if we push it up, it will be contained in D. It will converge. And in this case, we say that if such a sequence convergent to the limit surface exists, which lies consisted of surfaces entirely lying in D, we say that D is not L convex. But if for every sequence Sk convergent to S, the Sk with big K cannot lie entirely in D, then we say that it is L convex.
Yes, it's quite intuitive.
Yes. And now we introduce yet another definition. D is called weakly L convex at X if if the above holds for every surface S such that X is isolated point of this is intersection with the surface with the boundary, and S, the complement of S to X, lies entirely in D. Suppose we, yes, well, that's like this. But actually, okay, now let us state the following proposition. Proposition. It has two parts. First, let D be a domain of holomorphia, and X lies in the boundary. So let D be a domain of holomorphia. Sorry. then D is L convex. That D is L convex at each point x of the boundary. The next statement is the following. Let D be holomorphically non-extendable. At a point x of the boundary. Then D is a weakly convex. Weakly L convex at x. So let us prove the statement. So proof. So let us prove first statement. Let D be a domain of holomorphy. We have to show that it is L convex at each point of the boundary. Indeed. Take a point of the boundary and take a surface with this property. And take any any sequence of compact surfaces convergent to S with the boundary. Suppose the contrary, that the contrary to L convexity, such a convergent sequence can be chosen strictly inside D, and this complement is empty starting from such certain K. Then what do we get? If this complement is K lie entirely in D, then we can apply the previous Bianchi-Sommer continuum principle for the point x and obtain that the function f, which defines our domain holomorphy, should extend holomorphically to this point, to a neighborhood of this point x. This is contradiction.
Yes.
So now what's next? We would like to deal with a more general situation. So statement, so it's done. Is it okay if I don't write? Or should I write it down? Okay. Let us write this. Yes, okay. Yes, okay. Okay, okay. Let contrary. D is domain of holomorphy of function f and not L convex at x. Not L convex means that there exists an S through x. The boundary line is compact subset in D, and there exists a convergent sequence of compact holomorphic surface lying in D, such that Sk converges to S, and the boundary converges to the boundary. So then, by continuity principle, f extends to a neighborhood of point x, to some neighborhood of point x. But it cannot extend holomorphically because this is a function defined of the domain of holomorphy, and that's the end of proof. What's the first statement? So now, let us prove the second statement. Proof of the second statement. So, so D we suppose holomorphically non-extendable. This means that there exists, so the picture is the following. Here is D, here is X, and there exists a neighborhood U such that there exists a function f on the intersection of U and D. And we assume that this intersection is connected, and for simplicity, and that f does not extend holomorphically to X. And what we can do? Suppose contrary, that D is not weakly L-convex at X. What does that mean? It's not weakly convex. There exists a surface, compact surface through X, such that the intersection, such that X is isolated. I would like here to ask isolated point of intersection with the complement of Cn to D, like this. I need not only isolated as a point of intersection with the boundary, but isolated point of intersection of S with complement. I would like to correct that. Let me finish. Isolated intersection in S intersected with complement. And then the picture is like this. Here is S. So the punctured germ of S lies strictly inside U. And it is the limit of convergent segments of holomorphic surfaces. And we can apply the same argument, the previous argument, for the new domain, for the intersection of U with D, and for the function. And of course, we have to be honest, I have to take a precise compact surface inside, contain it in S with the same property, whose boundary is a compact subset of this intersection, and then to choose to cut from SK smaller surfaces convergent to this cut version of surface S, but it is easy details. So, and we have proved the proposition. Now, I have still some time, that's nice. And I would like to pass to necessary and sufficient conditions for convexity and for holomorphic non-extendability. Actually, there is a differential inequality on the boundary. If the boundary is the zero locus of C2 smooth function without critical points, then there exists an elementary differential inequality on second derivatives of this function, which guarantees, or which is necessary for convexity. It is an inequality on the so-called Levy form of the function. Levy form is one part of its second differential. So, definition. So let phi be, so let we have U a domain, and let phi be a positive function. Not positive, just real valued function of class C2. The extended Levy form of phi at a point X is the following. Is L is a bilinear form of type 1,1 on the tangent space. at the point x, defined like this. L of VW, L tilde of VW is the following. Is the sum of the squared phi dzs bar dzj times vj ws bar. And the differential is taken, the derivative is taken for the point x. That's the expression. So it is this form is bilinear over R. It is C-linear over each in the vector V is C antilinear in the vector W for obvious reasons. And I would like to say this is Hermitian form.
I don't really see. Do you have both indexes like J or?
No, one is S.
Yes.
So here is S. I'm sorry for this. And here is J. Here is S. So I'm sorry. Here is J. Okay. It is Hermitian form. This means that the matrix of these differentials is Hermitian matrix. This means that being Hermitian form means that d squared phi dzs bar dzg is equal to the conjugate of the same derivative with bar replaced from one variable to the other. That's it. Let us prove this. But I would like first to use a more general claim. Phi of z is real valued. Then we have the following relation. D phi over dz bar is equal to d phi over dz bar of everything. Indeed. Indeed. Let us so if the function is R-valued, then its differential is R-valued. Is the differential of complex linear vectors is R-valued. But we know that df at a point x is equal to d round f of x plus bar f, the other dividend, right, like this. We know this. Df of x at vector v is this linear combination. And this is identically real valued. And since this is identically real valued, this means so if it is real for every way, this holds if and only if df of v is the bar of this is identically equal to this. That's it. Because we have the following situation. Our differential, real value differential, is sum of C-linear part and C-antilinear part. This sum is identically real if and only if these two parts are complex conjugates. And this immediately proves this relation. This relation, where one can add the J here, with V being just unit vector in the G direction. That's it. Nothing special. And we have this relation, and let us differentiate this relation. So let us write down d squared phi dz s dz s bar dzg, right? It is since these are differential operators with constant coefficients, they commute. We go right down in the other order, dzj, dzs bar, right? They commute being the differential operators with constant coefficients. And what is this? It is d over dzj of the following. Of df, dφ over zs bar. And we know that this is the conjugate of the other. So it is d over dz bar, dzj of dφ over dzs bar, right? And now we again apply the same relation. So we have this. By the way, one moment. This is much. This is I have made here a small confusion because this relation is very general, actually. We don't need to have phi real. This relation is very general. The explanation is the following. Let us write down the differential of phi. The phi is d round phi plus d. Right? This is C-linear, this is C antilinear. When we take the differential of bar, we obtain the following. D phi bar is clearly equal to z, because taking differential is equivalent to pass to the conjugate function and to take as differential, because this is a composition.
When we go to parts like
yes.
an imaginary.
Yes, because this is phi bar is post-composition of phi with complex conjugation. And that's it. And this means that we apply complex conjugation to both parts. And when we apply complex conjugation to this, it becomes C antilinear. Mm-hmm. And we apply complex conjugation to this, it becomes C linear. And we get a composition, or we get the composition of the differential as the sum of C antilinear and C linear part. It's unique.
Oh, well, yes.
It's unique, and it implies this relation. That's it. And now we apply this relation to here, and we conclude. What do we conclude? It is equal to bar of.
So just it doesn't need a valued function here as well.
Yes.
It's just any function.
Yeah, yes. Any function. Yeah, yes. Yes, and we obtained this. Take for squared phi over the z bar, the z g bar, the z s. That's it. And so this proved that this form is Hermitian. And this means that it is changed to its complex conjugate when we permute the variables. It's equivalent. And now let me introduce invariant definition of extended Levy form. So, given a point x, given two vectors v and w in this tangent space, and let us take v tilde of z and w tilde of z, holomorphic vector fields. On a neighborhood, on some neighborhood of x, whose values are the given vectors at x. That's it. And now let us do the following. So let us define L, the form L of two vectors, like this. First, we differentiate in V. So we take a holomorphic part, C-linear part of differential, apply to V. So we differentiate at a variable point Z, and we apply this holomorphic part, C-linear part of differential, to the vector V of Z. And then this gives us a function, a complex valued function, right? And then we take its bar differential, it's the antilinear linear part of its differential, and we apply this at W of Z, to the vector of W of Z. And we evaluate this, take value at Z equals X. After this, all these both differentiations, we calculate the value at Z equals X. And what we get will be exactly the value of Levy form on these two vectors, independently on choice of these holomorphic vector fields. Indeed, let us prove that it is well defined, independent on choice of holomorphic vector field. The reason is very simple. Because here, the only problem which may arise is when you second differentiate, you will differentiate also this vector field. This will not happen because the differentiation is bar differentiation. It vanishes identically on holomorphic objects. D over the Z bar vanishes on holomorphic functions. And that's the end of explanation. And this implies the following important corollary. That notion of extended Levy form is invariant under by holomorphisms. And even the holomorphisms, corollary. Notion of extended Levy form is invariant, or rather functorial, under holomorphic maps. What does it mean? So consider a holomorphic map H. So Z is H of W. H is holomorphic. And let X be equal to H of Y. And we would like to send, so the statement is the following. The Levy form of the composition, we can take composition at a point X, Y. And we evaluate it two vectors, V and W, is equal to the Levy form of the initial function phi at X applied to the images, the H of Y V and the H of Y W. That's it. And this follows from this invariant definition, because that's how do the vector fields behave under the differentials. Because what you do, take this definition of Levy form in the image, and let us now recall. Now let us replace Z by a new variable W. What does happen with these differentials? If we precompose a function phi with holomorphic map, then the holomorphic part of differential of this precomposition will be obtained from the holomorphic part of differential of the initial function by precomposition with the differential of holomorphic map. Because the holomorphic part, so there is a chain rule of holomorphic differentiation of composition, provided that we precompose it with holomorphic map. The chain rule remains valid for holomorphic and anti-holomorphic part. And that's the reason why it's true. And when we do chain rule, this automatically replaces our vector v by its differential, by its image and its differential. That's it. So now we are, now we would like to introduce the true Levy form, which is related to a domain. Definition. So let phi. So U is domain in Cn, and phi is real valued C2, X is a point in U, and we assume that phi X is not a critical point. That the differential is not zero at X. Some partial derivative is not zero. So then we take a hypersurface phi. We suppose that phi of x is equal to 0. We take this hypersurface x, if x equals to 0, it will be regular near x by implicit function theorem due to non-vanishing of this differential. It will be regular. Let us take h, which is tangent. So let us take the tangent hyperplane. Let us denote this by gamma, and this is tangent hyperplane to gamma. And let H be the maximal complex subspace. So it is kernel, basically it is kernel of the holomorphic part of differential at x. That's it. Because, why it's true? Why it's true? Because of the following. So H is kernel of d phi plus d phi of x conjugate. So this is antilinear part because phi is real valued function. We have such composition. So it is kernel of the real part of the holomorphic differential, right? So this tangent, so it's not H, it is tangent to gamma. That's it. So the tangent hyperplane is kernel of differential. What is differential? Is sum of holomorphic and C-linear and C-antilinear. Yes. So the tangent space.
Why H is?
I will explain it right now. I have not finished. So first step one. Step one, we have this. We have a tangent hyperplane to this, and this is exactly the kernel of differential of phi. So yes, and what is differential? Differential is the sum of C-linear part of differential and C-antilinear part, which is its complex conjugate, right? And the sum of this and this is the same as the real part, twice real part of the holomorphic part. And this is C-linear, right? C-linear function. And we have hyperplane, which is a kernel of real part of C-linear function. And we know from previous lectures that this maximal complex subspace is the kernel of this C-linear function itself. If we have C-linear function, we can then its kernel lies inside the kernel of its real part, right? And, and the first kernel is the maximal complex subspace in the second kernel. We have seen then when we were studying the generalized maximum principle, etc.
Okay.
We were dealing general fact. Is it okay? So general fact. So alpha is C-linear functional on Cn. Alpha is not identically equal to 0. And then if T is kernel of real part of alpha, then H being equal to kernel of alpha is the maximal complex subspace inside T. We have seen this before, and that's the whole story. That's it, and that's maximal complex subspace. And now, definition. The Levy form of phi at x is the restriction denoted L is the restriction of the extended Levy form to H, to this kernel H. That's it. Now, what I would like to prove. I would like to show that this Levy form, thus constructed, is the form responsible for property of local convexity of domains. So we will be dealing with the following situation. We have domain D. We have a point X. And we have a neighborhood of X in which there exists a function phi, a real valued function phi, C2 with non-zero differential at X, such that the intersection of D with U is the sublevel set of the function phi. And therefore the boundary is zero locus of phi. That's the context in which we will work. Now I would like to state this theorem. I don't know whether we will have time to prove it, but at least we will state to fix our goals. Theorem due to Levy, Kshotska. Theorem is the following. Let L, the Levy form at X of the function phi, be positive definite. Positive definite as a Hermitian form. Then D is holomorphically non-extendable. At the point X. It's first statement. A second statement. Let D be L convex. At X. Then the Levy form is non-negative definite. That's it. What we would like to prove. So now let us pass to the proof.
So this two puzzle is
Yes.
a little bit like
There is gap.
even value, but not.
Yes, not exactly. Yes.
Okay.
Yes. So before we pass to the proof, let us prove some preparatory proposition. So from now on, we consider that x is the origin. That x is the origin. That's it. And we also consider that H is the coordinate subspace Z2, etc., Zn, for simplicity. We can choose such a coordinate in such a way. Proposition is the following. That phi of z is equal to c, to some c real part of z1 plus q to 0 of z plus high terms plus O small of z squared. Where q, this is a quadratic homogeneous polynomial plus L, the Levy form evaluated to the radius vector z, we put here, plus higher terms. That's it. Plus, and there is yet another term which I missed. Yes, plus it's called complex conjugate. That's it. And this number is real. It's real. So sorry, one moment. Let us write down it. In a different way. Real part of some complex constant times z1. It should be some real functional, like this. So the proof is the following. Let us write down a symptotic Taylor series for phi of z. It will contain linear part. The linear part will be like this, because H is a kernel of the homomorphic differential. So there is no problem with linear part, and then there is quadratic part. Quadratic part consists of several terms. It consists clearly of Levy form, and it consists also of homogeneous part in Z and homogeneous part in Z bar. It's clear that this should be conjugate to this, complex conjugate to this, because this is real valued. We know this is real valued, and this is yes, and then we have high terms. And this is nothing special. And proposition 1, proposition 2, one can kill.
The first proposition is like that we can write phi down in this way.
Yes, we can film this. Proposition 1 can kill Q2 0 by holomorphic change. So, actually, without loss of generality, it will be convenient for me to assume that C here, C is equal to 1 because I can rotate the coordinate Z1. I can rotate it and introduce new coordinate, right? And I can introduce the holomorphic change which does the job. The holomorphic change which does the job is the following. Z1. Sorry, where it is? Okay. And now we would like to, we can still do the following observation. We can erase all this stuff and we can write down like this. Because both Q20, it is complex conjugate, have the same real part. And if we sum them up, it is the same. It is the same as to take twice real part. And therefore, we have this plus Levy form. Holomorphic change is like this. Z1, Z2, etc. Zn is sent to exactly this, to Z1 plus 2 times Q20 of Z, Z2, etc. Zn. This is a variable change which does the job for quite obvious reason. Because this Q, if you substitute it to the Levy form, everything is fine because it completely contributes to high terms. And now we are ready to prove.
And the first proposition is obvious because
Yes.
we need some linear part, we need some quadratic part.
Yes.
The quadratic part
Are split into three terms. Yes. Yes. Yes.
To 0, 1, 1, and
Yes.
0, 2, and to
Yes.
0, 0, 2.
Yeah, exactly. Yes. Yes.
Yeah.
And that's it. So let me stop for this lecture right now. But we have already a necessary background for the proof of Levi-Strauss theorem. And now with this background, the proof is very short. By using the previous theorem by Benke, Sommer, etc. So, but we will do it next time. Okay. Okay. Да, Саша, есть у вас какие-то новости? Вы, наверное, были заняты сессией.
Ну, да, немножко было на процессе, поэтому я думаю, что я буду в пятницу.
Что?
В пятницу можно поговорить.
А, замечательно. Да, давайте в пятницу, да. Хорошо.
Какие у нас дедлайны по листкам второму и предыдущему задаче?
Ну, вы знаете, судя по тому, как происходит сдача, я думаю, дедлайна не будет. Главное, чтобы физически до экзамена все было сдано.
Хорошо.
Вот.
Это прекрасный вариант.
Вот. Я думаю, что по-другому никогда у нас более вообще.
Нет, первый листок я честно отправила Алексею.
А, замечательно, да. Да. Еще будет третий листок.
Ага. А всего будет 4?
Я не знаю, но три точно будет, а насчет четвертый я еще подумаю.
Вот. По поводу первого листка там такой вопрос.
Ага. Да, давайте.
Невозможно не до конца.
Да.
Там то ли опечатка, то ли...
Давайте.
Там, значит, в первой задаче задана форма...
Да, я помню это задачу.
Вот, соответственно, здесь...
Голоморфно.
Здесь вот эта функция голоморфно зависит от всех?
Да, от всех.
От всех.
От всех.
Просто если бы она зависела только от одной заджет, то, конечно, мы
нет, конечно, нет. А вот вся суть в том, что верно или неверно. Вот главное понять, верно это или неверно.
Нет, там, кажется, формулировка все-таки в первом пункте докажите, а во втором для всякого пути это верно.
Вот. Да, докажите, что если путь брать
да, нет, я понимаю, что там соль, видимо, в том, что мы берем сначала комплексное многообразие, а потом уже там берем путь. Вот, но я пока не... Ну, то есть, кажется, там просто нужно, чтобы измерялись кажется, можно удивляться подобного рода слагаемых ниже неравных, но я пока не понимаю, куда это взять.
Ну, на самом деле вопрос такой. Если вы считаете, что есть контрпример, придумайте хотя бы один. Потому что первый пункт он правильно говорит, что там, если у вас кривая лежит на вещественная кривая лежит на комплексной кривой, и по ней стягивается, то все хорошо. И мы, наверное, ему доказали.
Ну вот я пока дошла до того, что нужно очень равенство между вот этих вот...
По секрету скажу, в первом пункте это не нужно. Первый пункт это именно доказать.
Ну хорошо, да. Примеры.
А вот
там можно либо так, либо доказывать, соответственно, как-то достаточно долго и нудно, что исходная форма это дифференциал какой-то функции.
Нужно просто, вы в принципе изучили вот внешние формы, там дифференциалы и так далее. Ну вот если вы знаете эту теорию, в общем, знаний...
Ну, возможно, мне надо еще немножко учить.
Да, ну, так, стандартный уровень знаний, стандартный, в общем, набор знаний, в принципе, достаточно. Вот, там как ведут себя дифференциалы там, при различных операциях, там, не знаю. Если я скажу при каких операциях, это уже будет очень сильная подсказка.
Да. Нет, хочется все свести, конечно, к тому, что двойной дифференциал равен нулю.
Ну...
Используется теорема Стокса, как в классическом.
Ну, вот в первом пункте не случайно требуется, чтобы путь был стягиваем по голлофной кривой.
Понятно, да.
Случайно.
Как бы сильно намек. Ну ладно.
Вот, хорошо, подумайте.
Вопрос на поздно.
Но Стокса вы знаете, да?
Стокса я знаю.
Очень хорошо, да.
Нет, то, что там надо принять теорему Стокса, практически сразу очевидно, когда ты видишь стягивающуюся петлю.
Ну да, хорошо. Хорошо, тогда, в общем, решили...
Это просто я хочу, да.
Да, я второй Алексей.
Вы будете на семинаре?
На семинаре я какую-то часть времени буду, как минимум какую-то часть времени.
у вас будет сейчас что-то, да?
Вообще-то да.
Хорошо, но они принесут оборудование, да?
Да.
Потому что у нас тут мы постоянно
А,
видим,
забывают
что
люди оборудование принести?
да, не хотят, да, приносить и будут. Сейчас вот не выключают экраны, но я вот сейчас погасила. Надо все как-то, в общем, чтобы кто-то отследил, а никто не следит.
Да, ну они обычно все уносят.
Ну вы, если что, вы им напомните.
Да, конечно. чем лекция закончилась?
Значит, мы ввели формы и дошли до теоремы Глутсука. Ужасно.
Ну, а доказали ее или нет?
Нет, только чуть-чуть. Ну, доказали некоторые предложения, которые
Ну да.
быстро становятся доказательством предыдущей теоремы.
Так, тогда... Так, а на лекции кто-нибудь еще был? Нет, понятно. Алексей Антонович не говорил, придет он на семинар?
Но вроде собирался пойти.
Ладно. Так.
Я думаю, что можно начать.
Угу. Сейчас. Здрасте.
Вы начали уже?
Ну вот сейчас начнем. So one application of the continuity principle is erasing real singularities. Of holomorphic functions. So the statement is as follows. So if we take a domain in C2, and take a function, take a holomorphic function, take a holomorphic function on the complement to the intersection with R2, where R2 is a subset of points ZW such that the imaginary part of Z is 0, and the imaginary part of W is 0. Take a holomorphic function on this, let's call it F. Then F extends holomorphically to D. Yeah, so it we may assume that D is just a polydisk centered at 0 and of multi-radius delta delta. And we need to extend extend f to the origin. So the idea is to use the continuity principle.
So we need to fix some compact surfaces and then
Yes, we need to find a sequence of one-dimensional holomorphic surfaces which so we have this real subspace so we need to find a sequence of holomorphic surfaces which somehow approaches the origin.
don't intersect it.
Yeah, so S K holomorphic surfaces and Sk converge to S0 such that all Sk do not intersect this real subspace, and S0 intersects R2 at the origin only.
so maybe we can use pieces of parabolas, something like z1 equals I z2. And
Pieces of parabolas, right? So if our coordinates is so this is a good candidate for the limiting surface, right? Because and we just so to get a sequence of surfaces non-intersecting the subset, we may as well just shift everything a little bit in the imaginary direction upwards.
Is this for Sasha to suggest a parabola?
Yes, I think so.
Well, this idea was from this idea, so it's kind of interesting.
It was in tasks.
Yes, this idea was a hint to the problem, so still it's still not easy. Yeah, so I believe we just, to be compact, we just need to cut them.
Yeah, so we may take just
Yes.
Z to be in some small
So
disk.
then we have something like such pieces of parabolas, and they go down and down and down to this parabola which intersects it.
Yeah, so it's almost immediate that SK like this so SK intersects R2, does not intersect R2, and S0 intersects R2 only at the origin.
Okay, yes, so this parabolas, the limit parabola which touches the
Mm-hmm.
zero, and the complement of the limit parabola to this origin is lies entirely in the domain equation, right? Okay, and so to show that the function extends to the origin, and so how do you use the surface to prove this?
So what was the question?
So how do you tell me what the how do you use the surfaces to show that the function extends?
Okay, so yes, so we used the boundaries of this
Yes.
compact surfaces. So
Mhm.
in this case, it's basically themselves. So then we take the neighborhood of these boundaries, neighborhoods of these edges, and so Yeah, we looked at the gap between each of these pairs of these neighborhoods. So, and no. So we look at the gaps between these neighborhoods and the boundary of our domain. So D. This is example. And then, we used quadrant 2 and so the principle is like we see the gap between each neighborhood of this SK and between the boundary of our domain, and it's bigger than our fixed one, so we use the theorem.
Yes, that's true, but in fact, for purchase, I think one thing is directly the same in terms of principle. Because actually what you have for just a number right now, this is part of proof of principle. So what you can do just take this segment of surfaces and it satisfies the continuity principle, right? And by continuity principle, we know that each point of the unit surfaces, each point is each function in our domain space, right?
Well, yes, I just didn't understand that I may use continuity principle. Okay, so yeah, if we don't go into details of the proof, then we just use the continuity principle because we have compact surfaces which goes to the one compact surface, and we know that the boundaries have a limit too, and so all intersections with our two are yes, so our function is allotted on all of these surfaces, and so we continued.
Yes, just any holomorphic function. Any holomorphic function by the continuity principle extends to a neighborhood of the surface, and therefore it's 0. Yeah, so this was for 2 dimensions. Maybe let's think about a possible high-dimensional generalization of this statement.
So basically, we chose to, so basically we used D as this small quantities and extension to the origin, because then we may just move it all around and continue F to any real point.
Yeah, so so if we need to extend the function to any point of R2, we may as well just make an affine coordinate change, assume that our point is 0.
parabolas too, because basically we just need to we need some surfaces which don't intersect with our n. So basically we need just one coordinate not to be real and okay. So we take sum of squares plus this tk and multiply it by I, and then it will be not real coordinate.
Yeah, so in high dimension, we just so we have D in Cn, and extends to a holomorphic function. On D by exactly the same argument. Yeah, so so at the first glance, it seems to be straightforward.
Yes, I think it's the same argument. You just apply it in high dimension. It's the same parabola. Complex parabola. Okay, because this complex parabola lie in a slice, in two-dimensional slice, but the two-dimensional slice with R2 deleted lies in our domain. And therefore our parabola lies in our high-dimensional domains. Our limiting parabola lies there, so I don't see there is no problem with those.
Yeah, so just by slice you mean just take a complex C2. Yeah, we may take C2 and just intersect the whole image with it. And what we get is
there's two complex surfaces by
because these parabolas, which are complex homomorphic surfaces, containing in C2, they are by definition complex homomorphic surfaces containing in C2.
Oh yes, by definition. Because we have this reaction. Oh well, okay.
yeah, it's even easier.
So well, we work with C2 and nothing more.
This is the problem, just frankly speaking, the problem to extend the high dimension is a problem about nothing. Nothing.
Well, okay.
Yeah.
It's nice, well, okay.
Okay, so So the next problem is to check if a given domain is holomorphically non-extendable. Yeah, so to do that we should use a theorem which yes, the Levi-Kostka, which but not yet finished. We can still yeah, take it for granted and
okay, just so our function then is
are trying now to calculate the limit form, right? Are you trying to calculate the limit form of the function?
Yes, and
Have you managed to calculate it at some points?
not yet.
By the way, actually, this is a nice name. Maybe there is one special point in which it is easy to calculate. One special point.
Yeah, but I have given that it equals to 0, so
Can you write down the calculation?
I may write down calculation for what's that?
So have you actually computed the Levy? Have you actually computed the Levy format for any examples?
Yes. When I was looking at this problem, I have computed myself, but on some national kit.
For some what?
National kit on some.
Maybe it's the fact that our Levy form will be
Yes, of course.
Oh.
Our function is already
okay.
but we have to restrict it to the proper standard space.
Okay, so I just maybe I don't understand.
Yes, it is already a form. We have done so our function, first of all, our function is this is already a form type.
So
The extended Levy form is quite big. What about the Levy form? So if let's say extended Levy form is quite clear, which it is. Yes, this is
yeah, but it's just that I have a feeling that extended Levy form will be zero. So
No.
why?
No, because you have some d over zs, but
Yes, so it will be basically like.
Because s and j may coincide, the indices may be the same.
Okay, then I. Okay,
The indices in this form were the same indices.
okay, so then I need to. I didn't understand that they may coincide. But if they may coincide, then it will be. Okay. Yes, so I need to add. Oh, let me swatch. Of course. Я не понимаю, как...
Can you just extend it a little?
Okay, yes. This one. В общем, вот эти части забирают все. Готовая единица. Которая все вниз, потом включаем.
Yes. That's it. Okay. Yes, that's correct. And now we have to restrict this in order to obtain the true form. We have to take a point, a base point in the boundary of D, just the simplest point. For example, we can take.
Okay.
We choose
Maybe
take.
sign a point.
Yes, you can take your favorite
Okay,
point of
so-
the boundary, and you can restrict the linear form to the tangent space.
Okay. So.
You should have just quickly take this as
Okay, I don't
base point,
need
and then-
any point.
yes,
Okay.
and then you have first to find.
So I may take something like 1-0,
Exactly. Yes,
for
one zero.
example. Okay. Okay, so in 1-0. So there. So it will be. Ну, то есть basically I need okay, so my tangent space will be something like that, да. Мне просто смотреть не показательно, что можно просто
Yes, you have to calculate the differential of the function
Да,
and take it as a holomorphic function.
не, сейчас.
It's good.
Вот. Соответственно, вот это будет мое
But that's right.
касательное пространство. Да.
That's right, yes. And let us restrict the Levy form to this space. Actually the tangent space is just the space equivalent parallel to the W axis.
Yes.
Yeah.
So all my z's will be equal to.
Zero. Because your vector, tangent vector to this
Oh,
space.
okay. So
Yes.
all my vectors. All my vectors. What's happening? Okay. So. Yeah. So this. Okay. So if I restrict. To z equals 1, and assume that the first part is equal. The first part equals to 0, and then the second part equals to. Oh well. I believe it. Well, basically it may be any number.
So it means that this is tangent space. Let's calculate the differential at this point. The z equals yes. Yes. It's actually one is minimum for the modulus of the boundary, right? Because it divides the inequality. Yes, and so therefore,
Well,
the uniform is
This first part is
vanishes.
vanishes, and this part may be
Yes, so,
any number.
yes, and so we can equip our tangent space with coordinate W, and we can write down just this and this. And so that's it's minus. And so it is a quadratic form. If you restrict it to V is equal to W, then it will be minus modulus of V.
Yes, so
Square. So it's negative.
I believe it will be
Negative definite, right?
negative.
Yes.
Okay, so, and then by theorem it's not holomorphically extended.
It is not a domain of holomorphy. It is not holomorphically non-extendable at this point.
Yes, because if it's holomorphically non-extendable, then it positively.
Yeah.
Then it is positive.
Okay, and then and so you have calculated the uniform. You have made your analysis at the given point. Can you prove that the same holds at any other point of the boundary without extra calculation?
Okay, so
Because property of holomorphic non-extendable is invariant under holomorphism, right?
okay, so I have my boundary is one sec. My boundary is invariant under rotations.
That's right.
So
Rotations, yes.
so then if if I proved non-extendability in one point, then
Extendability, because here is your uniform is negative.
Yeah, so
Therefore, it is extendable. Holomorphically extendable.
extendability. Yes. And then so I may just rotate this point, and then I will receive extendability in any
Orbit, in any rotation.
in any rotation orbit. Yes.
Multiple of the other points, which are not rotation measures. This is the hint is that this domain has already been a kind of seed before.
Yes. Didn't remember that.
No, a kind of similar domain has been seen before. And looking at this domain, you can find
So I need to prove that any point which lies on the boundary
Yes.
is extendable.
is extendable. Yes, that's you have to prove.
Okay.
And
so
then maybe you can reduce it to the calculations you have done. Maybe you can prove. You can reduce to the case of your special point.
Okay, I may just hold near the same computations for real points, real
It's possible.
with such equation, right? And then by rotations, I may go to any point.
To any point, yes.
Such modulus.
Actually, it's possible, but I would like to say that we have been studying different group of automorphisms. Doesn't it look like to have a big group of automorphisms, bigger than rotations?
Well, rotations, and I multiply rotations by. Where's the
By permutation, it is not enough.
Yeah, permutations.
It does not show that any point can be sent to this file format. But actually, that's true. Can we describe a group, just some of the basic groups which acts on this domain?
So, okay, it's invariant under permutations.
Actually, the group is equation.
Yeah, so this function is a quadratic form of signature 1 minus 1.
Okay.
Yeah, so if the group preserves this form,
Okay, so okay, it's invariant under rotations. It's not invariant under permutations, basically, because
But we have something about group of automorphisms like such a form.
maybe I forgot.
Yes.
Okay, so
Just several lectures ago, we were dealing with the group SU11.
yes, was
Or just
you want. And well, I don't remember.
Sorry?
I'm sorry, I don't remember really.
But because this is actually the boundary is the sphere, satisfies the equation is the pseudosphere. Modulus z square minus modulus lambda square is equal to 1. And we have seen that on this sphere, the group
Okay, it was.
acts transitively.
Yes, because it's basically a conus.
Yes, exactly. Yes,
Okay.
it's something
Yeah.
inside the
Yeah, and it was, it's something like, how the special Minkowski matrix.
Exactly.
I just need the picture. Yes, so we have this special Minkowski matrix there, and it's in some sense, it's 10 and it's still here.
Yes, and actually we can
We have this constant, it adds transitively, so we may just say that we will rotate that.
Yes, and if the domain were slightly more complicated, then we would have
Well, I may just, So if the domain is more complicated, I may try to change coordinates.
You can do the same calculation because it's calculation at any other point will be not much more difficult than this. There will be just slightly different description of starting from scope extension space, but the argument is basically the same. Express without the z from in terms of w along this substitute everything to the equality.
Yeah, and a slight variation of this. So what if we just change this condition into this? Then, well,
Yes.
basically the same case.
But we may just say that then we just permutate our coordinates and it will be the same, no? It it equals to
So it was z squared minus w squared less than or equal to minus 1.
Mm-hmm.
then it will be, I believe.
Yes, and that's the same. And what about, yes, yeah, I agree,
Mm-hmm.
that it does always important stuff.
Okay, so
But what about if, but now I would like to solve this argument reduces the problem to the previous one.
Mm-hmm.
But in the case, suppose now the model z squared minus model z, model w squared is less than or equal to 1, not minus 1.
okay.
Yeah.
So like that, okay.
Mm-hmm.
What can you say in this case?
Okay,
Yes.
so this one holds because it's still the boundary. So all of these computations are
Mhm.
right, and we even have the same point, and we have the same tangent space.
So it was less than or equal to 1.
We still have
Calculation. Yes.
Yes,
Yes, we can do
phi
that.
holds, and this point is still in the boundary, so tangent space is the same. What about these calculations? They hold because phi holds,
Yes.
so we still have such linear form, and basically it seems like nothing changes.
And before it was the same inequality but with opposite sign. Before.
Yes.
Yeah, so the last step. So when you restrict the form to the boundary, so what do you get?
Maybe the same. It's just like I have a ball and I have point, not a ball, basically that. Okay. What is it? Bounce. Right.
Mhm. Yes, I think the argument should work. Yes.
Mm-hmm.
Well, basically nothing changes because I had like interior of like we have this curve like modulus that squared minus modulus w squared
Mhm.
equals 1,
Mhm.
and as d we take interior or exterior of
Mhm.
this curve, and the boundary nothing changes.
Mhm. Yes. Yes, actually it is interesting because it may sound strange. So the cone, if one draws our cone naively, the cone is z squared minus w squared
Mm-hmm.
Equals
equals the cone, and the cone is like this, equals 0, right? If I would like to do less than or equal to 1, then actually you do the following. You take something like this, and you do what is down, what is down,
Okay.
what is down. Okay.
Mm-hmm.
And yes, actually, one could imagine that there are good reasons that it is not convex at all. So this is down. But if you study the other inequalities, z squared minus w squared is bigger or equal to 1, then the situation is different. You have to take this part. But in the naive picture, this part sounds to be convex.
Mm-hmm.
But here it isn't. Actually, your argument shows that it isn't convex.
Yeah, because the form is not positive definite.
Yes. But in 3 dimensions, it is convex.
It is convex, yeah.
Mhm.
So the thing is that
So that would all these
real pictures are
Yes.
very dangerous
Yes.
in complex cases.
Okay, I think that's. Oh yeah, that's it.
So, Alexei, is there somebody who already presented you to you the solutions of the second task? Of the second task?
Второй.
Второй листок.
Да, значит, вот Андрей Жижин сдавал. Так, вы тоже что-то прислали?
Да.
Первый.
Это был первый.
Вы только первый листок. Сейчас, и что-то еще Миша Трошкин присылал, но надо посмотреть, что.
Очень хорошо.
Да.
Кто лечит из иностранных участников сдает на англоязычных?
По-моему, нет.
Нет, да?
Я еще раз посмотрю в почте, может, я кого-нибудь забыл, но, скорее всего, нет. Сюда ходил какой-то китайский студент?
Да, ходил одно время китаец, потом еще китаянка, одна китаянка, потом вторая китаянка. И вроде